Okay. Hello, everyone. It gives me great pleasure to introduce Ningning for this evening's invited talk. Ningning is an assistant professor at the University of Toronto. If you look at her webpage, you'll be surprised at the number of publications she has there on a wide variety of topics. On the way here, someone, I won't say who, one of you, said that almost anyone has written a paper with her. So in case you haven't, you can line up there at the end of the talk and ask why. But anyway, I'd like to introduce you, and thank you for coming.
Yeah, thank you for having me, and thanks for the very nice introduction. And thanks for everyone, thanks everyone for coming to the talk. And my plan for today is to talk about a recent popular programming language notion called algebraic effect handlers. And I will start by giving an overview of what algebraic effect handlers are, why they are useful, and how to use them. And then I will briefly talk about my recent work on a combination of algebraic effect handlers and parallelizable computations. So let's get started. Since we are at Zurich, I suppose we all love functional programming, where programs are easier to reason about. But in practice, we also interact with the real world. For example, if you program do some input and output from the command line, it reads or writes to files, or your program might throw an exception, or it might use some mutable resources, or you might want forms of concurrency and backtracking. However, while effects are everywhere, in many programming languages, effects are often ad hoc and hard-coded, in the sense that they are implemented separately, and it's really difficult to change the behavior of them. So how should we do this better? Well, the first thing that comes to mind must be monads, of course. We will get back to this when I briefly compare monads and algebraic effect handlers later in the talk. Instead, in this talk, I want to convince you that algebraic effects and effect handlers provide composable and structured control flow abstraction that allow us to define and use effects in a flexible way. Algebraic effects and effect handlers are a relatively new concept from the community, where algebraic operations are introduced by Plotkin and Power in 2003, where they established the categorical semantic foundation for algebraic operations, which, roughly speaking, are a family of operations that satisfy certain algebraic laws. While algebraic operations allow us to construct, combine, and reason about effects, they did not tell us how to handle them. So later, in 2009, handlers of algebraic effects are introduced by Plotkin and Pretina, which are used to give semantics to algebraic operations. So roughly speaking, algebraic operations and handlers are the constructors and destructors of effects. In recent years, there has been a growing interest in effect handlers in academia. For example, this paper from PLDI 2021 presented an implementation of effect handlers inside the OCaml compiler, with the main motivation being to support asynchronous I/O able to express highly scalable concurrent applications. And the implementation has been integrated into the OCaml compiler since OCaml 5. And this work from last year, from UPSA 2022, presented a high-level interface for writing effect handlers for C++. And they have presented various examples, including cooperative literate threads, actors, generators, etc. And more recently, this work from UPSLA last year discussed an implementation for effect handlers for WebAssembly, in order to support non-local control flows. And they have presented a prototype implementation in reason time. Since we are at Zurich, I also want to mention a field work that comes with effect handler implementations in Haskell. So this paper from SFP 2013 is a position paper that aims to popularize effect handlers, and they won the Test of Time award at SFP last year. And they has presented a few implementations of effect handlers in Haskell implemented in various different ways. And at Haskell Symposium 2015, this work used a notion called freer monads to implement efficient effect handler implementation. Well, Jan Lehen and myself also presented an effect handler library at Haskell Symposium 2020. And 1 year after this paper, we also published another paper at ICFP that slightly generalized the semantics proposed in this paper. And we also come up with a second implementation. So the second one is a bit more general, but can be less efficient in certain cases. And one of the most popular effect handler library on Hackage is probably fused effects. It combines ideas from a few research papers, and last night I checked, it has already 10,000 downloads on Hackage, so you might want to check it out. On the other hand, it's not only about academia. There is also a growing interest in effect handlers in industry. For example, Semantics is a code analysis service at GitHub, and they use effect handlers in their production. And React is a JavaScript library for building in the user interface, and they use effect handlers to design hooks that allow developers to reuse stateful logic. And Pyro is a Python library by Uber, and it uses effect handlers for creating new inference algorithms for probabilistic programming. In particular, folks at GitHub and a few others, they wrote a paper at SAP 2022 and described how they apply a variety of programming language techniques in their development of Semantics, the code analysis service at GitHub. It's not only about effect handlers in this paper, because they also talked about other programming language concepts like generalized LR parsing, data type a la carte, and recursion schemes. But specifically about effect handlers, these two paragraphs are taken from this paper, and I'm just going to read them for you. An example of the utility and flexibility of algebraic effects is an effect we developed to extract telemetry data from our production Haskell systems. In a production context, we wanted this data to be uploaded to an aggregator. In a development context, we wanted to see them reported on the command line, and when running automated tests, we wanted to discard them entirely. And algebraic effect handlers allow us to achieve this easily, so an effect can be handled differently in different contexts. So I hope so far I have convinced you that effect handlers are useful, but I haven't really told you what effect handlers are and how to use them. So let's look at algebraic effect handlers through an example. So on the top of this slide, I have defined two effects. So choose is an effect that has a single operation choose, and the operation takes a unit and returns a Boolean. And similarly, exception is an effect that has a single operation fail that takes a unit and returns a polymorphic type A. And with this effect signature, we can already start writing programs using effect operations. For example, we can define a program that tries to toss a coin. So the program toss takes a unit, and then it performs this operation choose by providing an argument unit. And if choose returns true, we are going to return heads, or otherwise we are going to return tails. And interestingly, from the type signature of toss, you can say that toss says, I'm a function that takes a unit and returns a toss. That's some data types that has only heads and tails. But more interestingly, I have in this type signature the effect information. So that means that toss is a program, when evaluated, may perform effects, including choose, and maybe some others in this epsilon, and we don't care about other effects for this program. And with algebraic effects, it's also very easy to use multiple effects in a single program. For example, if you are drunk and you still want to toss a coin, So this program, Drunk Toys, says that, well, since you are drunk, tossing a coin may fail. So I'm going to first perform this choose operation. And if this choose operation returns true, then I'm going to toss this coin. Or otherwise, I'm going to call fail directly. And in this case, the type signature of drunk toss says that I am a program, when evaluated, can perform effects in both choose and exception, and maybe some other effects epsilon. And we will get back to this, but the specific order between choose and exception does not matter in this effect signature. So with effect signatures, we can already start using effect operations in a program. But we haven't said what would happen when an operation is actually performed. Because the semantics of operations are given by effect handlers. So an effect handler tells you basically what happens, well, in this case, this is a handler for exception. So it tells you what happens when the fail operation is performed. So it has an operation clause for fail, as well as a special return clause that is applied when the computation returns normally. So in this case, this handler maybe fail turns the computation type into a maybe data type. So the fail operation says that, so this implementation is basically just a function that takes two arguments. X is the operation argument we provide to the operation. In this case, it's just a unit. And K is the continuation, capturing where the operation is performed to where this operation is handled. And in this case, we just ignore this continuation and say we will return nothing when the fail operation is performed. And the return clause says that if the computation returns normally, let's wrap this computation result X inside just. So on the right of the slide, I have some examples. If we handle just this value 42 with this handler maybe fail, then this is where this return clause gets applied, so we will return just 42. If you perform an operation fail, like in this case, by providing the operation argument, a unit in this case, then we are going to apply this operation clause, which turns the whole program into nothing. And this is a handler for the exception effect. And similarly, we can also define handlers for the choose effect. So in this case, the true choice is a handler for the choose effect that says, if you ever perform this choose operation, let's just resume the original computation by always returning true. And this is implemented in this operation clause by calling this continuation K, providing this argument true. And in this case, this return clause does nothing. It's just an identity function that returns the original computation result. So now if we use this handler to handle 42, we'll just get 42. And if we use his handler to handle the toss program that we have seen in the previous slide that says if choose returns true, we are going to return heads, otherwise we are going to return tail. We are going to return heads because the choose operation from this program is going to return true. But more interestingly, because we have this continuation available, a handler may choose to resume the original computation multiple times. So this all choices is another handler for the choose operation, and it says if you perform a choose operation, let's resume this computation twice, once with true and once with false, respectively, and let's concatenate the results together. And if the computation just returns normally, then let's wrap the computation inside a singleton list. So now if we handle 42 using the handler all choices, we will get back a list, a singleton list with just the 42. But if we handle the toss program with all choices, then we are going to get a list with both heads and tails, because the original computation is run twice, with choose returning true and false, respectively. So with those examples on this program, we have seen how a single effect in a program can be handled by handlers. But, well, as we have seen, we can have multiple effects in a single program. Then we needed to apply multiple handlers to handle this program. And this is easy to do, as we just need to compose several handlers to handle this computation. So in this example, we handle junctors first using the handler with maybe fail, and then the handler all choices. Because maybe fail is going to turn the computation result into maybe, and all choices is going to turn the computation result into a list, so we get a list of maybes. And in this case, we get all the results, all the possible results back in a list. So we got just the heads when the first and the second choose return true. And we get just the tails when the first choose returns true and the second choose returns false. And we get nothing when the first choose returns true. So this is how we get this program result as a list of maybes. But with effect handlers, we can also very easily swap the order in which we apply handlers. So instead of applying maybe fail and then all choices, we could also do first all choices and then maybe fail. And in this case, we will get a maybe of a list. But since fail is performed in this program, we will just get nothing back. So this example shows that we can very easily combine multiple effects in a single program, and we can also nest and compose handlers in different orders to handle effects in a program, and we may get different results by applying the handlers in different orders. So having seen the examples, let's get into a little bit of the formal semantics of effect handlers. So don't get scared, because we can really summarize operational semantics of effect handlers in just these 3 rules presented on this slide. So the language we are talking about here is basically just the lambda calculus plus 2 more expressions. One expression for handling a computation with a handler, and another expression for performing an operation by providing an argument to a certain operation. And the first reduction rule is the familiar beta reduction rule that says if we apply a function to a value, then it just evaluates to the body of the function with the argument x substituted by the value b. And the next 2 rules are about effect handlers. So when we handle a computation using effect handlers, there are 2 cases. The first case, the computation might just return normally without performing any operation. And if the computation just returns normally, then at this point, we are going to first get the return clause from this handler. And let's say the return clause is just f. And we simply apply f to the computation result v. If, on the other hand, the computation performs an operation, it performs an operation op by providing the argument v, then at this point, we are going to handle this operation using the innermost corresponding handler for this operation. And this concept of innermost corresponding handler is expressed using the notion of what we call evaluation context. So the evaluation context, this capital E, roughly speaking, is just an expression with a hole inside it, but it tells you where you should look into when you are evaluating a big expression. So the definition of evaluation context says, well, I'm either empty, or, so this is where we have this hole. Or if you have an application, then we should first evaluate this function. If the function is already a value, then we should evaluate the function argument. Or we could also evaluate inside the handler. So this is call by value, of course, but the concrete semantics does not matter here. We could also do call by name. And going back to this reduction rule, it says that if you perform an operation, I'm going to handle it using the handler edge, with the knowledge that this handler edge is the innermost corresponding handler for this op, because no other handlers inside this evaluation context can handle this op. So this is expressed using this notion op, not in b-op of this evaluation context. And this handler edge, on the other hand, should handle this operation. And we handle this operation by first getting this operation clause for op from this handler. And this operation clause f once we get it from the handler, we are going to apply it first to the operation argument v. So this v is the argument we provide to the argument, to the operation, and then a function that represents the continuation we captured. And the continuation captured in this case is, again, the continuation from where this operation is performed to where this operation is handled. And it reinstores the original handler inside this continuation. And this is helpful when you have, for example, a list of stateful operations. You do a sequence of set and get, and you want to make sure they are all handled by the same handler. So these 3 rules, they really summarize the essence of algebraic effect handlers. I would also like to remark that this particular way of representing the semantics of algebraic effect handlers are sometimes called deep handlers in the literature. And this refers to the fact that inside this continuation, we reinstore the original handler. And there are also other variants of the semantics presented in the literature, and one of them is called shallow handlers, and it means that in this captured continuation, we do not reinstore the original handler. And people have shown that this pattern is useful, for example, if you have like a producer and consumer pattern, and you want to use this continuation as the computation that is waiting for or is producing the next resource. But deep handlers and shallow handlers can encode each other up to some definition of equivalence. So they are equally expressive. It's more a question which style you prefer for your particular implementation. And there's also other variant that I don't quite see often, but it exists. And it's a combination of shallow and deep, so it's sheep. And it expresses the fact that when you capture the continuation, you don't have to reinstall the original handler, but you have to install a handler for this particular operation. So you can swap out a different handler for the corresponding operation. And another thing I would like to remark is that sometimes people also formalize the semantics of effect handlers using what we call parameterized handlers. And this is like a generalized semantics of effect handlers in a way that each handler can now be associated with a stateful resource. So now every handler can have S, which is some stateful resource associated with it. And when the operation gets handled, this operation clause from the handler is now applied to the current state of the handler. And when you resume, you can also provide a potentially updated resource for this handler. So with parameterized handler, it's very easy to implement stateful handlers like get and set operations. Since we are talking about effects, there are also effect type systems that tries to keep track of what kind of effects a program can perform to make sure that all effects from a program have been handled properly. I'm not going to go into the details of the typing rules, but as you can see from the typing judgment, which says that under the typing context gamma, an expression E has some type A and may perform effects in this epsilon. So we keep track of the effect information of a program, and if you perform an operation op, and if we know op is associated with effect label L, we want to make sure L appears in the effect information. And ideally, if you have a handler that handles an effect label L, then we want to remove it from the effect information in this expression E. And also, other remark that I would like to make is if you read effect handler papers and effect handler languages, you will also notice that people keep track of effects in different ways. For example, F is a research programming language with built-in support for effect handlers, and it's the first research programming language, I think, with built-in support for effect handlers. They keep track of the effect information as sets. So this allows you to naturally use the notion of subset to use a program with fewer effects in a bigger context with more effects. But more commonly, you will also see languages using row types to keep track of effects. And there is also a difference between simple rows and scoped rows. And these two particular typing rules I presented here corresponds to scoped rows, which basically says we can have duplicated labels in the effect information, and it is helpful in certain situations. So that summarizes the formal semantics of effect handlers. We have seen the operational semantics, and we have seen its type systems. So we will look at one more example that is slightly more complicated, which is lightweight cooperative threads. And this is just to show that we can actually express lightweight cooperative threads in a pretty easy way, in a language with effect handlers. And to implement lightweight cooperative threads, we just need to define effect with two operations. So yield is an operation that takes a unit and returns a unit, and the fork is an operation that takes a computation, and the computation takes a unit and returns a unit, and the fork returns a unit. And the scheduler is a program that takes a computation to be scheduled. And it handles this computation by a handler for this co-op effect. And the yield operation basically says that if a computation wants to yield, then I'm going to put the current resumption into the queue. So we assume there is some effect for putting things into a queue and also get things out from a queue. We are going to put the current resumption into the queue, and then we are going to get the next available computation from the queue, and we are going to run the next this available computation. And if you want to fork a computation G, then similarly, we will also put the current resumption inside the queue, and we are going to call scheduler to schedule this computation G. And if a computation finishes, this is where we apply the return clause. And if it finishes, then we are just going to get the next available computation from the queue and run the next available computation. So let's assume there is always a computation available in the queue. And with the scheduler program, we can already write a program that has complicated effects like print and fork and yield. I'm not going to show how this program actually evaluates, but with this implementation, you can verify that all those letters, they're actually going to be printed in the alphabetic order. So we are going to print A, B, C, D, E, F, G. As you can see, we are mangling with the control flow in a pretty complicated way. So this summarizes the essence of algebraic effect handlers, where we have algebraic effects that define a family of operations, and we have effect handlers that give semantics to operations, and we have seen that effects and handlers can be composed and combined in a program. And as I said, I want to briefly return to the question, how do we compare monads with algebraic effect handlers? So there is a paper from Haskell Symposium 2019 that compares monads, and especially monad transformers, with algebraic effect handlers. And the conclusion from this paper, as I understand it, is that algebraic effect handlers can be a bit more modular when you program, especially if you have nested effects and handlers. Because if you program with monad transformers, you will have to lift an effect if you work with a stack of effects. While with monad and monad transformers, they can use to more easily express what they call scoped effects, which basically says that if you have like a very long program and then in the middle you have a block of transaction and you want to say if an exception is thrown inside this transaction, I want to roll back all those stateful operations inside this transaction, but not the stateful operations before it and not the stateful operations after it. And for those kind of scoped effects, it's easier to express using monad and monad transformers. So with that, now I want to get into the second part of this talk, where I would like to talk about my recent efforts on a combination of effect handlers and parallelizable computations. So to demonstrate the issue we try to solve, let's look at another example with effect handlers. Let's assume that we have an effect signature for a writer that has a single operation accum. And the idea is that we want to accumulate all the integers that have been passed to this accum operation. And we can write a handler for accum, and in this case, let's use parameterized handlers because it's easier to keep track of the stateful resource that we are writing to. So with parameterized handlers, the accum clause says that I am a function that takes 3 arguments now because I take the current handler state S. And I'm going to simply resume the original computation, but now I'm going to update the handler state to be S plus X. And the operation result is just a unit. And if the computation finishes, I'm going to return the computation result together with the list, with the state as a tuple. So we can now write a program like this. We want to handle this program using the handler accum with the initial starting handler state being 0. And this program should return as a tuple the computation result unit and the final state 3. But from this example, it's already clear that you will have to run this sequence of operations sequentially, because they are writing to the same stateful resource. So now, a question we would like to ask is it possible to run operations in parallel? And especially if we want to support user-defined parallelism behaviors, because we want to support user-defined semantics for effect handlers in general. And this is challenging, not because of these 2 operations that are writing to the same stateful resource, but also if you think about how this program evaluates, you will notice that when we handle this first operation, the continuation captured by the first operation will have the second operation inside that continuation. And you don't know how that continuation is going to use this second operation. It may call this continuation once, or it may call it multiple times, or it may not call it at all. So it's difficult to predict how many times the second operation is going to be run. And since we are talking about parallel computations, well, the first thing we should decide is the notation we want to use to express parallel computations. And in this work, we borrow the notation, the full expression from this paper at SFP 2021 that introduces a programming language called DEX, which is a functional programming language for array programming. And it has a notion called full expression. And the idea is that this full expression is going to build an array. So it's a little bit different from full expressions in languages like C or C++. For example, with full expression, we can write a program that increments every element inside an array. So inc is a function that says I take an argument x. And x is an array with n elements. So n is the length of the array, and the element type being integer. And I'm going to return another array where every element in the array I'm going to return is the original element from this array x plus 1. So if we call inc on this array 1, 2, 3, then we will get back 2, 3, 4. And more interestingly, DEX also supports some kind of effects inside for expressions. So for example, we can also write another program that sums an array. So sum is also a function that takes an array with length n and type integer, element type integer. And it uses this run accum to try to accumulate all the elements from the array into a stateful result. And it uses this variable y to keep track of the stateful resources, and we are going to build an array. For each iteration, we are just going to add the element from X to Y. Because run accum also returns a tuple with the computation result and the final state, and we use second to project out the final state. So if we run sum on the array 1, 2, 3, we will get back 6. But the interesting fact about this program is DEX is able to run this for expression in parallel. Well, the whole idea of for expressions inside DEX is they can be run in parallel to build an array. But in this case, we're actually also writing to a stateful resources. But the key reason DEX is able to run this in parallel is because while this Y works like a stateful resource, we can only do additive contributions, like we can only add things to Y. And you can never read the value of Y inside the iteration. So it's more like a writer. So there is no data dependency between the iterations of these four expressions. So you will be able to run this expression in parallel. But at this point, run accum is the only effect that is supported inside four expressions in DEX. So then a natural question is, how can we support also other kinds of effects inside the four expressions, especially we want to support user-defined parallelism behaviors. Before I describe our approach, I would like to take a stop and consider what kind of properties we want from a system that combines effect handlers and parallelizable computations. Well, we first want this system to be extensible, so the user should be able to extend the system with new effects. This is in contrast to DEX, which only has one built-in effect inside four expressions. And we also want to support user-defined parallelism semantics. So the user should have control over how the effects are actually handled inside parallel computations. And just like we want to compose and combine multiple effects in a program with normal effect handlers, we also would like to combine multiple effects even if the program is run in parallel. And our system supports all these three features with the key idea being that we designed a system that combines effect handlers and for expressions, and we interpret for as an effect. If we interpret for as an effect, with our language, you will be able to write a program like this. So you can use the accum handler to handle a program that has a for expression inside it. And inside the body of the for, we are going to accumulate some elements. And after this for expression, we are just going to return the string down. And we are handling this computation with the initial handler state being 0. And in our language design, this accum, all those three iterations, we will be able to run them in parallel. Because we consider for as an effect, now every handler in our system is also responsible for implementing an additional clause, which we call the traverse clause, that handles the for expression. And the traverse clause takes 4 arguments now. It is for parameterized handlers. For its non-parameterized, then it takes 3 arguments. And those 4 arguments are, well, n is the number of iterations, and s is the current handler state, and l is what we call a body continuation that I will explain shortly, and k is the original computation that takes the result of the for expression and resumes the original computation. And inside this handler definition, we are going to first run the body continuation, and then we do some unzipping, we do some reduction, and finally we resume the original computation with some state and some results. Well, to more closely demonstrate how traverse actually helps us run 4 expressions in parallel, we can look at the detailed derivation of this particular program. Where we try to accumulate every element from an array, 1, 2, 3, and after we are done, we are just going to return the string down. So if we are going to run this program, the first thing we are going to do is, because we have this for expression, and we consider for as effects, so it is going to be handled by a handler. So this whole program first evaluates to the traverse clause that we take from this handler haccum, and it takes 4 elements. I also have the implementation of traverse. It takes 4 elements. First 3 is the number of iteration, the length of the array. 0 is the current handler state, and then an array of what we call body continuations. As you can see, each body continuation is just exactly the body of this for expression, except that we push the handler to be inside the for expression, the body of the for expression. And each index now in this index ranges from 0, 1, and to 2. And K is just the normal continuation that takes the result of this for expression and resumes the original computation. And again, it reinstores the original handler because we are talking about deep handlers. And in each case, we are going to be able to provide a potentially updated handler parameter. We can go through the evaluation step by step just to show you how the program evaluates. So what happened first is we are going to evaluate each of these body continuation. But now the difference is that because we have pushed the handler to be inside this body of the for expression, now each of this body of for expression, they are effect-free. In a sense, all effects have been handled. So now we can run this array of body continuations in parallel. And in our semantics, if the for expression does not have any handlers surrounding it, it will be, and it is effect-free, then it will be run in parallel. And in this case, it will return us an array of results, and each result is a tuple with the original computation and then the final state. And in this case, 1, 2, 3. Because we are running the body continuation providing the initial handler parameter 0, so we get back the final state for each body continuation as 1, 2, 3. And then we are going to do some unzipping. So now results is just an array of units, and out is an array of the final states. So we get 1, 2, 3. And we have assumed some function reduction that adds all the results together, and we get the result 6. And then we are going to run the original computation with updated state, in this case 6. And also the results, in this case, is just an array of unit, and that get ignored by this continuation. So we continue the evaluation of the original program, which then gives us a tuple with the computation result done, and then the final state 6. So with this example, hopefully it becomes a bit clear that how we actually handle for expressions using handlers, and how the body of the for expression can actually be run in parallel once we push the handler to be inside the body of the for expression until they become effect-free. I'm going to go very quickly about the operational semantics, but really, we only added one more rule to the original semantics of effect handlers. So the first 3 rules are the rules you have seen already, but we only added the 4th one to present the case when a for expression is handled by the innermost handler. In our system, all handlers handle for expression. So this is just the innermost handler, not the innermost corresponding handler. So this is expressed using the notion of pure evaluation context, which is similar to evaluation context, but it does not have handlers in it. So this handler H is the innermost handler that handles the for expression by taking out the traverse clause from the handler and apply it to the number of iterations and the array of body continuation L that we constructed here, and then the continuation that takes the result of the for expression and resumes the original computation with the handler reinstored in both cases. And this is the only operational semantics rule that we add to the system. But with this idea, we can actually express lots of interesting examples. Writer is one example we have already seen. We have described more examples in our work. So one example is weak exception. So it's a weak exception. So this is our old exception effect, and we have a handler now for it that with the additional traverse clause. And the idea is that you can have exceptions in your parallel computations, and you can, and one of the threads, one of the for expression, the body of the for might fail. But even if one iteration fails, it does not affect the other iterations. So all the iteration will finish running, and once all of them come back, we are going to check whether one of them throws an exception. And if one of them does, then we are going to return nothing, or otherwise we are going to resume the original computation with the result of all the iterations. So this is helpful when you have exceptions in your program, but you don't specifically care about the exception in one thread because you want to finish all the parallel computations anyway. And just like you can combine different effects for normal effect handlers, you can also combine multiple effects for parallel effect handlers. So this is one example where we have a program that does both accum and fail in one of the iterations. And we are going to handle this program first using exception and then using accum. And in this case, the first accum is going to be accumulated by the edge accum. And then there is, when we are running the third iteration, because we start with 0, of this for expression, we are going to throw an exception. Nevertheless, because this is weak exception, so all those iterations are going to be wrong anyway. So we will also accum 0, 1, and 3, and 4. But since we have an exception here, the continuation after this for expression will not be wrong. And this is why we get, as the final result, a tuple of nothing and the final state 9. We also provide Haskell implementation for the semantics I described. I don't have time to talk more about this implementation, but I just want to remark that we also have a runtime tracing system that tells you at which point the effect is handled by which handler and how the for expressions actually get to run in parallel and when the results from the for iterations are combined together. So there are more things that I did not cover in this talk, which you can find in our paper. So the paper is currently under review, but we wish to put it up sometime soon, hopefully by the end of this month. And we have more examples from the paper. We support non-determinism in parallel computations, and we support pseudo-number generation. So you can use random number generations in the body of the for expression. And we also have a relatively more complicated example with parallelizable shared states. So all the threads are still being able to share a certain states. And if one thread trying to read from the state, it could block the evaluation of the other threads. And we also come with a type system with proven type soundness. And the main challenge of the type system is once you push the handler to be inside the for expression, during runtime, you actually did not know what type of this for expression it actually has. So the handler has to be more polymorphic in the type of the computation it handles. So that's all I have. So in conclusion, we have talked about algebraic effect handlers, where we have algebraic effects with that defines a family of operations whose semantics are given by handlers. And we talked about a new combination of effect handlers with parallel computations. And I also have a list of resources here in case you want to know more about effect handlers. So we have this effect bibliography that has the softwares, languages, libraries, papers about effect handlers. And Mattia Pretina has a tutorial paper on introduction to algebraic effects and handlers. Highly recommended. It talked about the semantics and comes with lots of examples. And it also talks about the F programming language. And Sam Lindley talked at OPLSS about effect handler-oriented programming. So the lecture notes and the videos are available online in case you're interested. And Dan Lehan and myself gave a tutorial at SFP 2021. And the tutorial is more about the Coca programming language we were developing. It has effect handlers and also some other features. And finally, if you are curious about where the word algebraic comes from, when we talk about algebraic effects, you can read this paper, What's Algebraic About Algebraic Effects and Handlers, and it touches gently on the categorical semantic foundation of algebraic effects and handlers. And that's all I have. I'm happy to take questions.
Hi, thank you for the talk. I really enjoyed it. I barely knew anything about effect handlers before this, and I'm more clear.
Now you're an expert.
It's clearer now. Yeah, well, maybe not. So what I want to comment on is something that maybe is a bit nonsensical, but it came up to my head when I was looking at. You've introduced traverse as a necessary operation for all handlers to have for you to support for. And I thought, traverse, okay, traverse lists, but then as a Haskell, I thought traversable, an abstraction. So you can traverse more than lists. At a certain point, I thought, okay, so you augmented the list of operations that the effect handler has to implement to support one more operation and their consequential non-determinism, and etc. Effects that you'd like. And I was wondering, to what extent can you have, say, an effect handler of an effect handler? What I mean is, say that your effect handlers are, the reduction semantics are basically defined by the handlers of the effect handlers, if that makes any sense. In the sense that basically you can, say brackets, you have some list of effects, and then the list of all the operations that each effect handler within that list must implement is defined by the outermost effect handler that defines which of operations each handler must have to implement. Does that make any sense? Maybe not. Maybe I'll write it down and then I can show you.
I think that sounds like an interesting idea. Like, I have never thought about that this way. It sounds to me like a combination of sort of like you want to define the behavior of the handler so that it can be used to handle parallel computations. Exactly,
such that traverse is something that you've, as a user, define that every handler must implement. And then you also have, as a user, to guarantee that that's type safe, but that's another problem, right?
Yeah.
Yeah, that is it.
Yeah, I think that's interesting.
One observation in particular is when you were showing the list of reductions, it felt like a bit like the reduction were a handler for how you'd handle that reduction. I will think about how I can phrase this better.
Okay, yeah, thank you. I think it's an interesting comment.
Thanks a lot. One question about the pseudo-random number generation. Now, if you do that, do all the different threads, well, I shouldn't probably say threads, but all the different parts of the array, do they all get the same random number seed, or if not, if they all get a different one, which I would hope, but how do you avoid making it all sequential again? Because then you have to somehow initialize it different ways, or yeah, how does that work?
Yeah, that's a good question. So first, you get different seeds for each of the iteration, and how we achieve that is, do I have the backup slides? Maybe I do. Yes, it's complicated, but I didn't ask him to ask this question. But basically what happens is before you call this body continuation, you will split the key. And if you split the key, then you can provide different keys to each of this iteration.
Okay, but then they all have to wait for the splitting key. Yeah.
Yeah, they all have to wait for this splitting key, but the computation we are parallelizing is this like else. Like this part will be parallelized, but this part does not. You will have to do something before that happens. Yeah, thank you.
Just a really quick comment. When you were talking about the sheep embedding, or whatever, Leonard Augustin talks about like deep and shallow embeddings of EDSLs, and he calls things that are in between neritic, which is a biological word relating to the shallow part of the sea. So just that there is a prior art for in between deep and shallow.
Well, that's good to know. Thank you.
Hey, thank you for the wonderful talk. I had a question that is actually somewhat in the vein of what Rodrigo here asked, which is, it seems that one of the advantages of structuring effectful computation with effects and handlers is that you can choose what handler to use for an effect when you want to run the effectful computation. It's not hard-coded, right? So you want to have like a queue, you just pass H a queue and you say handle with this such and such computation.
Yeah.
And you also mentioned that the parallelism that you had is user-defined, but the way the parallelism is handled is defined in the definition of the effect, it seems.
It's defined by the handler.
Right. So is it possible to then change out the way the traverse is done, but keep the same handle from one execution of the handler to another? So you have the same handle, but you do the parallelism in a different way. So for instance, one time you want to limit it to 4 threads at a time, say, and another time you just let it go with as many as you want and so on.
Yeah.
Is this possible with...
So you can, like for example, for the random generation case, you can define other handler for this random effect that does maybe some of the operations differently. Maybe you just run all the iterations using the same seed, for example. You can do that. So you can then also swap out the handler you use to handle the operation and also the traverse.
Right, of course.
But maybe your question is also related to maybe you want to have the same definition of this operation, but a different operation for traverse.
Right, yes. You can, because what you're saying is possible in the sense that it's almost the same handler and you just copy it, kind of. But it's in the same vein of like, do you have a different handler for traverse? Like a handler for the handler?
Yeah.
Yeah, it was just a thought in that direction.
Yeah, I think it's currently not supported, but I think it's a good idea that you can decouple basically how the operation is handled and how the traverse or how the full expression is handled. And it's maybe similar to the handlers of handlers idea.
Yes.
Yeah.
And on that note, another thing, is it possible to make traverse the fundamental operation where you have handle right now? I think everything is defined in terms of handle and traverse desugars to like traverse over a for desugars to various uses of handle. Is it possible to have a calculus like this where traverse itself is the fundamental primitive and so everything is done in parallel? And then handle just becomes traverse with one element on that list or whatever structure.
Right. I think it's an interesting direction to think about. One potential challenging, though, is that you may want to have different traverse semantics for different effects.
Right.
So you may not have a single traverse handler for the whole program, but maybe multiple traverse handlers that defines how each effect is handled differently.
Right, that makes sense. That makes sense. Yeah. And lastly, is there any... okay, maybe we can actually... I can ask you questions about this later. But yeah, thank you for the wonderful talk.
Thank you.
Okay, good. There's time for one question, maybe?
At the beginning, you mentioned other effects also, like reading and writing files, network calls, time-based operations. That's in Haskell are in I/O. do you support all these also? You mentioned sort of maybe, but all the others are also supported with your concept.
I didn't quite catch the question, but all the examples presented on the slide, including the examples before the parallel part, they are supported with the parallelism semantics. I mean, in a sense, all effects are supported because the semantics of traverse is provided by the user. So the user can do whatever they want in terms of how a for expression is handled by a certain handler.
Okay.
Thank you.
Thank you.
Oh. I think I may actually want to ask the same question. It seems that in the semantics, everything was interpreted in terms of continuation passing style. So it's easy to do things like readers and writers and throw exceptions. But how would you do something like a network call or writing to the disk?
Right. Is this question about the effect handlers or specifically about the parallel part?
Not about the parallel part. It's about the semantics of the effect handlers.
Right. So you will need, in the end, in a language, some mechanism to deal with like input and output or network calls. It's just like, for example, things you can do with monads in Haskell, you will still have to define how I/O is actually implemented for Haskell inside the compiler. But effect handlers are more like we provide a machinery for the user to implement some non-local control flow in ways they want, and especially if they want the effect to be handled differently in different contexts.
So would you say that in the same way that the I/O monad hides the interaction with the real world, the interaction with the real world is also hidden within one of the implementation of an effect handler?
For certain handlers, yes. For certain effects, yes. Like for example, in Coca, one of the research languages that has built-in support for effect handlers, we still need to define how actually printing and reading are done inside the compiler. But other than that, the other part of effect handlers, they are really just the user-defined semantics, and they are wrong using the operational semantics that we talked about. So there's nothing magic.
But does that break the referential transparency of the semantics?
Well, if you have side effects, in some aspect, I guess so, because you have to do some printing. But I guess this is more like a way, like similar to monads, that are used to support computational effects. And once you have computational effects, I think it's difficult to talk about referential transparency because you are printing to the monitor that we will be able to see it from the monitor.
All right, thank you.
Thank you.